Today we'll be covering few advanced topics related to SolidWorks simulation. We'll learn about the solid shells and beam meshing in a single assembly. We'll learn about the frequency analysis, and we will learn about the thermal analysis that is incorporated. So without any ado, we'll begin. So this is the particle separator that we'll be solving today. It has all the three kinds of elements in a single assembly. So the bottom structure will be the beam. The top structure, as you can see here, will be meshed in shells, and these brackets that you can see here will be meshed in solid elements. So we'll start with the simulation, but before that, whenever we are defining shell elements, I would like to tell you that we will define the shell elements on a single phase. When we are selecting the surface, you need to be very precautious while selecting the surface. So in this particular case, if you can see, this is cantilever beam, and the user has selected one as the bottom surface, one as the top surface. This is how you can discriminate between them. The bottom surface is indicated by orange, top surface is indicated by gray color. So what it may result in inaccurate results. So as you can see, the top surface, if we are applying a load on a cantilevered beam, the vertical load. So the top surface may experience some tension and the bottom surface may experience some compression. But since we are unable to define them properly, the results may come inaccurate. So you need to make sure that you are uniformly defining each and everything in the surfaces. And also, as I've already told you, that the beam properties will be considered in the background. So the sectional properties, whatever required for finding out the bending stresses or the torsional stresses or axial stresses, those will be considered in the background, and we'll see this kind of representations on the beam. Also, on the very first day, I've told you that the beams and shells will have 6 degrees of freedom, that is 3 translational and 3 rotational. So now we'll begin with the training. So I have one study already solved here. We'll solve from the beginning. So go to simulation, create new study, create static, let's say particle separator. Click on OK. So our study has been created now. Now we need to define the material. So we'll define a common material to all. But prior to that, if you can see here in the window, if I expand this, you can see there are several solid bodies present, and there are several surfaces. So I know from the experience that these surfaces won't be of any use to me. So I'll simply exclude them from the analysis. Now we need to define the shells. So as you can see, the symbol is set to as solid. So we need to define shells with these particular particle separator, which is having some thickness. So in order to check the thickness, we'll simply take the section. Yeah, so we'll take the section and see what kind of thickness are we dealing with here. So evaluate, click on here. So it's almost 2 mm. In case everywhere else the thickness is 2 mm, so I can directly go and apply that thickness on a surface. Okay, so most of the thickness are in 2 mm, so we can go further. I'll simply isolate this body to be able to work on it more properly. So in order to define the shell now, I'll select this, each and every body, right click on it, so define shell by selected faces. So here are 3 components, as I've told you that when we define thin, thick and composites. So if the length to thickness ratio is greater than 20, at that time we go for thins. If the length to thickness ratio is less than 20, then we go for the thick. And if in our assembly we are dealing with multiple number of laminates, at that time we use composites. And in composites, we can also set the orientation of the laminates. I'll set 2 here, select the appropriate face. You can also select multiple faces which are involving this thickness. And from here, you need to define from where you want to offset this. If I take this view, and if I offset it with this, that is middle surface. So the surface will be created on this, the shell elements will be created on the selected face. half of the thickness will be interpolated outward, half will be inward. So we don't want that. We want the thickness to be interpolated on this inner surface. So for that, I'll select bottom surface. And this is how we can create this. So click on OK now. Then the shell, as you can see here, the symbol has been changed. We need to define the material, so I'll simply add the material to all as plain carbon steel. Okay. So then let's define the thickness for this now. As we will be treating these brackets as the solid, so we won't be applying any thickness to them. So let's apply the thickness to this component. So in this, you can see there are two thicknesses involved. So this is 2 mm and this top flange, it is of 3 mm. We need to measure it accordingly. So I'll simply right click on this, differential selected faces, click this face, 2 mm, offset by a bottom surface, pin this, click on OK. Now I will select this, the thickness is 3 mm, 3 mm. You can see it has been translated the surface thickness to this side. That is, the data has been captured properly. Click on OK. Now the next thing. So we need to find where. Okay, here. So there are several bodies which are still not having any thickness now. Like this. Apply thickness. Select as 2 mm. Offset by bottom surface. Click on OK. Define thickness to this. 2 mm. This. Offset by bottom surface. Click on OK. These two bodies are still remaining. Right click, define shell by selected faces. Select the appropriate faces that we want to apply thickness to. Select these 4 faces, select this one. Also, since even though it is showing this as a different body, we can still select it. No issue with that. 2 mm, offset by bottom surface. Okay. This flange is of 3 mm, so I'll define the thickness accordingly. Okay, so all the shell elements have been defined. Now you can see the symbol has been changed to shell elements here. And the tick indicates that the material is also been applied. The next thing is to define the solid elements, solid beams. So I'll simply exit isolate. I will treat all these members as the beam elements. So as soon as I treat them, the uniform cross-sectional properties will be considered in the background, and so we did not worry about it. So I'll simply multi-select all of them. So all these bottoms frame members, we will be keeping them as solid. Now I'll right click on this, say treat as selected bodies as beams. So those beam structures would be converted to beam elements. Also, one thing you can notice here is when I have created the beams, one more folder has been introduced here, that is a joint group, and the beams are connected to each other at the joint. So if the beam is being connected to 2 or more beams, the joint will be in pink color. If the beam is free, it will be in yellow color. So you can apply the loads or fixtures on the joints as well. So the next thing is to define these shells for these plates. Go here, just define shell by selected faces. Select the outer face. You can select any face you want, but make sure that you are selecting the face, and you have to apply the load on that very face only. So the thickness is 5 mm. Select 5 mm here. We can treat them as thick shells. Offset. Click on OK. Now the next thing is, since we have defined multiple elements or structure simulation, we need to define the appropriate contacts for them. As if in the first day, very first day, I've told you that if the assembly consists of only solid elements, a global bonded contact can be applied to all of them. So no need to define any external contact until and unless if no relative motion involves between them. But if relative motion is there, we need to define contacts. So in this particular case, since we are dealing with multiple components or multiple elements, we need to define the contact accordingly. So I click this pin, this, select this beam, and select the face on the shell surface shell where I have defined the shell element. Click OK. Similarly, this beam, this surface. Click on OK. Similarly, this beam, this surface. Click on OK. We have to connect the beams to these bottom plates which are in solid. I'll select this joint, this surface, click on OK. This joint, this surface, click on OK. This joint, this surface, click on OK. This joint. Reselect. This. Okay, this one is remaining. Mounted this joint, select the joint, select appropriate face, click OK. So now the joints have been connected. Now we need to connect the solids to the beam elements. So we need to connect these brackets which are solid to these beam elements in order to software to understand that these are connected. So I select the beam in this. Okay. Select the appropriate solid, click OK. Similarly, select this beam, the solid, bottom surface of that solid I'm selecting. If for solid, you can select any surface, but on for shell elements, you need to select the surface on which you have defined the shell element. Now we need to define the contact between these solids and this shell, this and these solids. So I'll do that. Contact set. Select bonded as the face. Select the larger surface area in the bottom, smaller surface area in top. Here, select other. Okay, we'll reselect it motion. Okay, now let's see if we are able to solve this. Before that, we need to apply the proper loads. So I'll first apply the fixtures on the bottom side of these plates, as these will be mounted on the ground, and they will be mounted, since I can see a hole here. So obviously a bolt connector is going to there, maybe a foundation bolt. Okay, I can use that as well, but the purpose of this particular training is not to show you that, as I have already shown you. External load with forces. Now you need to define the force. So this particular particle separator, the particles of some maybe dust particles or some grains would come from here. The gases will be removed in the upward direction, and the particle will be separated and collected at the bottom. So this plane must be connected to some other plane, and since we are not considering the part in this area, we will consider the reaction forces developed by that part, which have been predefined. So on this particular phase, the load is going to be in direction 1. So I'll select this phase, selected direction, define particular plane, let's say this plane top plane. So the forces will be in the reference to this top plane. In direction 1, I'll select 45. Direction 2, I'll select 75 Newton. If I pin here, I can see the direction in which the forces are going. I want one force to be normal to this. So I'll skip this and stay at 45 Newton in the reverse step. Okay, this shouldn't be there. This will be 75. Okay, so now we are good to go. I'll simply change the direction of this force. This kind of loading we can observe. Click OK. It is telling me to select a shell entity. Since we have defined shell on this phase, it needs to be selected. So I'll simply delete this and reselect this. So now our shells have been defined and we can move forward. Click on OK. Now the next thing is to define a load of 150 newtons. Since this particular area is not having any supporting structure below it, so we can go for this. Select the beam, select this, the direction. So I'll consider this as the reference. The direction will be downwards. Load 150 newtons. Click on OK. So that's now I think we are done with everything. Simply mesh it. We are going with the curvature based mesh. Click OK. I think our meshing is done here. So let's see we are able to get any results, or the solver will tell some errors with respect to this. So quickly run this. So we can see it has run quickly, but it is showing that this particular surface or these two surfaces are not connected. So we need to define some additional contacts between them in order to make sure that they are connected properly. Also, in case of beam elements, whenever we are introducing beam elements, those won't be shown because you can plot the beam elements separately. So if you click right click here and define stress plot, so you get multiple options whether to plot solids and shells and to plot beams. So in case of beams, you can plot bending axial as well as the torsional stresses. So I'll say upper bending axial and bending, these two faces I'll plot separately. So this is how it will show. But since our structure is not properly fixed, we need to first fix it, then rerun the study. So I'll add one more contact set. This particular edge will be maybe welded to this, or maybe Okay, it is telling me to select a shell entity. So by default, by mistake, the upper edge has been selected. So I'll select the bottom edge of the select. I think now it is intact and we can rerun the study. So our analysis is completed and it is showing a maximum stress value of almost 20.2 MPa at this particular phase where it is selecting the beam. So we can go with, okay, one more thing we can do is add an gravity load. Consider the weight of this particular assembly. So I'll simply right click external loads, get gravity, select the phase. So this will be my reference phase. So with respect to this, the gravity direction will be downward. Click OK. And again, run the study. I think we have considered all the loads in this particular assembly. Most all the possible loads that can act on this. So maybe we'll get some different results this time. Let's see. So as you can see, after introduction of gravity, we have the load has been increased to 30 MPa at this particular location. So we can say yes, since we have applied all the load, we can go with this. Also, it is showing me this value of deformation scale. So the results are only scaled. If I plot displacement here, the value is quite low. Now we'll see the stresses on the beams. So it is showing me upper bound action and bending stresses as close to 10 MPa. I can say it is pretty much safe structure as compared to the yield strength of this material that we have chosen. So this is how we can do this. Now we'll move to a PPT. Okay. So this was about the usage of solid shells and beams in single assembly. Now we'll see or learn about the frequency analysis, how it is done. So basically, this particular formula you'll learn in the dynamics of machineries in maybe in the third year end or final year. So basically, this is the equation of motion that we use to solve the dynamic problems. The first is the mass matrix here, which is This is defined as the mass matrix, which is multiplied by the acceleration. So d double dot is the secondary derivative of displacement. This is the viscosity matrix, and it is multiplied by the velocity, and it is the stiffness matrix, which is multiplied by the displacement itself. So combination of all three will be equal to the external force that is acting on the body. In case of frequency analysis, we don't consider any kind of damping. That is why the viscosity coefficient is 0 in this particular case. So we will only consider mass and stiffness matrix. So since we are considering the basic assumptions, that is loads are changing very slow, the static assumptions can be used if the frequency of the applied load is significantly lower than the first natural frequency of the structure. If not, if this particular first natural frequency, that will be finding out after this particular example. If not, at that time we need to go for dynamic analysis and required to introduce some maybe damping in the structure in order to capture more accurate results. So I'll walk you through the basic example of the tuning fork. You need not, it's okay if you don't practice on this. This is only for the purpose of understanding how to actually define loads and what procedure to follow while solving the frequency analysis. Let's quickly move to SolidWorks here. Close this. Open. Open the file. Return. I think it's in the day one. Yeah. This is the example that we'll be solving. We'll be simply applying the fixture here, and we'll see what kind of frequency does it gives us. So I'll start new study, select frequency from here, okay. So the material has already been applied, and since we have single part, no need to define any connection. You click on fixtures, select fixed geometry, do this face, and simply mesh it. And run this. So as you can see here, it has solved it very quickly. So in case of frequency analysis, these values are of not much importance. This is only the indication for where exactly the displacement might happen, and you need not refer this value. The only value of importance is the mode shape values, that is the frequency that we are getting. So different mode shapes, if I go on searching for, the frequency values are changing, and this indicates that if this particular frequency is achieved, the structure may behave in this particular way. It is the assumption. It may not behave considering the other load factors that are introduced. So this was about the frequency analysis. Now, since we have applied the fixture, we'll try to solve it without fixture. We'll copy this, name it as without fixture. Click on OK. I'll simply suppress this fixture here and rerun the study. So now you can see, since there is nothing restricting this, it is vibrating in space, and that is why it is developing zero frequency. If we move add further modes, it may show you some frequency value. So if I go to frequency here, we can list out all the resonant frequencies that are present. So these are the 5 mode shapes we have asked for. So 5 probable displacements values that we can expect, and accordingly it has shown as the mode shapes. Similarly, in this particular case, a list resonant frequency. So for first 4 mode shapes, there is no particular frequency. After the 5th mode shape, the structure may start behaving like a let's say rigid body, and it may introduce some of the fixtures due to its stiffness, and we may experience a frequency. Okay, so we will see one more scenario where we will be applying a load on this particular tuning fork. Let's see if we can get any difference when we are pre-stressing the tuning fork. So I'll simply copy this, name it as pre-stressed. Okay. I fix this now. Again, apply a load of, let's say, 450 newtons. Okay. Done this. You can see the frequency has been drastically reduced. So if we were to compare the results from all studies in this configuration, we'll simply compare the first mode shape of first and third study. As you can see, we were getting to when it was free, the frequency was around 228. When we applied the load on it of 450 newton, the frequency is almost reduced by half. So when we are applying, this can be concluded in saying like that when we are applying the load, the stiffness of the component may increase. So if we were to find, okay, so you are going to learn this in the future related to when studying dynamics of machineries or in vibrations. So natural frequency we indicate by omega suffix n is equal to under root k by m raised to 0.5 to indicate under root. So this k is stiffness factor, is stiffness, and m is the mass. So as we increase the stiffness, suppose we are applying the load, so obviously the stiffness is going to be increased. Since we are increasing the stiffness, the natural frequency is going to increase. So that is what we are doing here. So moving on to the next thing. Yes. Now we are going to introduce an assembly, and we'll be solving that assembly for this simulation purpose. And in this also, I'll show you how to run the multiple studies involving different boundary conditions. So in this particular study, this is the engine block which will be mounted on some structure, and we won't be considering the engine block as we'll be applying the remote mass of this. So only the mass properties of this particular structure will be considered on this frame. We will try to solve or reduce the meshing for this particular solving in order to more efficiently solve the problem. So also one more thing to note down, as in case of frequency analysis, we don't introduce no penetration contact, as introduction of no penetration contact makes the structure stiffer, which directly results in increasing the natural frequency. So in order to capture more appropriate or better results, this provision is not there. Okay. So I have two studies already solved. I'll simply walk through the steps that will require, and we'll run for multiple studies this time. I'll create new study here, create frequency, okay. The material, okay, the material is already, okay, it's not applied, so we'll apply the all isolate material to all. Okay. Okay, we'll apply plane curve still. We'll consider the global bonded contact. Now we'll apply the remote mass of this. So the mass properties will be considered. Meshing will be done on this. Expand this engine. Right click on this. Say treat as remote mass. Select the mounting points where the mass will be transferred. So these four will be the mounting points. Okay. So you can see that it is turned transferred. That means the mass properties are already considered, and the meshing won't be done on this particular part. And you can see one more folder is here, stating remote mass. Now we will apply. Okay. First, we'll have to apply the contacts. We'll be considering the boundary contact between the assembly. In order to make sure where exactly it has considered the boundary contact on its own based on the global contact, we will see. Right click on this and select contact visualization plot. Create calculate. So all the locations indicated by red indicates that the contacts have been created at these locations. So we need to define some additional contacts to other locations. Where exactly are those? Okay. Okay, so we need to define between contact between this beam, this beam, this beam, and this beam. And so close this. Right click on connection, define the local contact in contact set. Pin this. Select this space, this space, this space, this space. Select this space, this space. Click on OK. Similarly, select this space, this space, this space, this space. Click on this space and this space. Click on OK. This space. And okay, no need to deselect this as we have already defined contact here. So we'll define contact, one more contact. Okay, so I think we have applied all the context in this. Let's see if some parts are flying off or not. Without applying any fixture, we'll simply run this to check if all of our parts are connected or not. So this is called as the free run to make sure that assembly is connected. Okay, so since we have considered the remote first, it has not meshed it and shown the results on the bottom file only. So let's see how it is behaving, whether some parts are flying off or not, or it is behaving as a single. Okay, so it is moving with a single assembly. So no parts are flying off. That means everything is connected. So now we can apply the fixtures, appropriate fixtures to it, and rerun the study. Like this, fixed geometry. Okay, and again rerun the study. So we are continuing the result. The first motion is observed at 154 hertz. So this was about it. So now we will rerun it. Okay, here. So it is showing some exaggerated results. If I animate this, I'll be able to see the movement if it crosses near. So this kind of trend we can expect if the assembly goes up to 154 hertz. But it may not be the actual deformation, considering we are only considering the frequency loads. In actual scenario, there might be some other loads involved in this mechanism. Now, one more thing we can do here is, so you can see these locations, these beams. Originally, they must be connected with some bolts or some pins with the bottom plate. In order to incorporate that as well, we can do. So I have a predefined study here. Each and everything is defined. Only I'll show you this new thing. So here I have defined pin connectors to connect the top and the bottom blocks, top beam and the bottom block, in order to consider the actual condition that can be used. And whenever I am using the connectors in my SolidWorks simulation, using the bonded contact is not of any use, as it may result in inaccurate results, because all the composed surfaces will be glued together, and usage of pins is unnecessary in that case. So if whenever I'm introducing pin connectors in order to consider the more accurate actual scenarios, I should always consider allow penetration in case of frequency analysis. If we are going for static, we can use the no penetration contact. So now we'll just run this study. Also, there is one more study. This is the same as the study I've created here. So I'll run multiple studies here. So to drop this down, say run all studies. So it will rerun all the studies which are not ran. Okay, so as you can see here, the studies have been solved. I'll simply close this. Now we can see the results. So let's compare the results between the two. So in this tab, I can select compare results. Select all studies. I'm interested in finding out the first mode shift. No need to select each and everything. Click on OK here. Okay, one thing is remaining in this particular study. We haven't applied any fixture. We'll have to do that. That is why it is showing 0 hertz as the frequency. We'll quickly do that. Geometry. Select this way. Select this way. Click OK. Rerun the study. It will take a couple of minutes to solve. Okay. What is happening? So I think we found this problem related to this. Let's see, does it give any wrong results, or do we have to make any further changes to this? So you can see one of the pin connectors is flying off. We need to restrict its motion. Okay, so similar condition can be seen here. If I animate this, it will show me some components maybe flying away from it. It has considered the fixture for one phase only. Okay. 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 I think everything else will be solved now. Okay. So, okay, one thing you can notice here is it is penetrating to this. I don't think, because since we have applied allow penetration at this phase, so this may be the issue, and it is allowed to penetrate. But since we have applied the board characters, pin characters as well, so we can say that this may be the actual conduction that is occurring, or the frequency in this particular case is lower. So if we are going to find the in terms of the resonant, if we are considering the safety, so we should consider this value and not the frequency that is being defined here, as we have only defined the bonded contact in this particular case. So the structure is more stiffer if the frequency is 154. This may not be the appropriate way. The lower value of the frequency you should always consider in order to check for the resonance. Okay, I hope you all understood this. Let's move to the next slide. So in this thermal analysis, we'll be learning about the concept of conduction, convection, and radiation, and how you can apply those on this particular example of a microchip. So in this example, we will be applying a heat power to this heat sink. So some heat power will be applied. Microchip and the connectors will be open to atmosphere, and heat transfer will take place through them. Prior to moving to the SolidWorks part of it, let's just go through a few of the basic things. So thermal analysis is analogous to structural analysis in a way that when we define displacement or find out displacement, in thermal analysis we find out the temperature or conduction. So it's not actually the temperature; it is only said like that. The thing we are finding out is the conduction behavior. When we are dealing with the strengths in structural, we find out the temperature gradient, that's the rate of change of temperature with respect to displacement. When we are finding the stress, we find out the heat flux, that is the heat per unit area transfer, heat transfer per unit area. When we are dealing with the loads in structurals, we apply the heat source or heat sink, that is heat power in our this particular case. Whenever we are applying the prescribed displacement, then it is similar to prescribed temperature, since heat displacement is analogous to temperature. Elastic support as convection coefficient and elastic modulo thermal conductivity, that is Q. So basically, thermal conduction is the heat phenomena when it takes between whenever two surfaces of solid which are in contact with each other, and this is the basic formula to find out this conduction due to heat transfer due to conduction. So it is equal to negative of, since heat is going to be always decreased from high source to low source. That is why it is negative. K is thermal conductivity. A is the area of cross section of this particular interface. T hot is the hot side from which heat is doing, that is source. T cold is a sink, and it is divided by L. So the total thickness of the solid from which heat transfer will take place. So this T hot minus T cold by L, that is dT by dx, we can say, is the temperature gradient. These are the few thermal conductivities of some typical materials. So insulators are always going to have lower thermal conductivity, whereas pure metals will have the highest thermal conductivity. Then comes to the convection. So wherever there's a solid to fluid interface going on, so solid is hot or fluid is cold, or like that. So at that time we use the convection heat transfer for calculation purpose. So it is equal to HA. H is the heat transfer coefficient, which is defined by the dependent on many quantities like the temperature of the fluid film, or what kind of viscous behavior it is having, or what kind of with what velocity, speed stream velocity it is flowing. A is the area, Ts is the surface temperature, and so I think I have. Yeah. Okay, so this is the particular formula that we use for to find out the heat transfer due to radiation, which is equal to sigma, that is a Stefan-Boltzmann constant, times the emissivity of radiating surface into the area, that is the surface area on which the radiation will take place, or from the area where it is emitted. Ts is the surface temperature, Tf is the ambient temperature, and it is raised to the power of 4. So this is some advanced thing that we consider while in terms of radiating surfaces. That is, we find out the shape factor. It totally depends on the type of or the shape of your structure or surfaces. So if you are having some curved surfaces, the shape factor may be different for those, and if you are having some planar surfaces, the shape factor may be different. So it is also called as radiation view factor. So it is basically a fraction of thermal energy leaving the surface of object 1 and reaching a surface of object 2. So that is, suppose in this particular case, this particular brick is the radiating surface. So whatever the radiations are emitted from this to this surface, determined entirely on geometrical consideration, that is based on its shape. A multiplier to the radiation equation until limitless ranges between 0 and 1. So this will have the if it is like in the straight line, the radiating factor will be 1. If some uh, other material is in between them, which will reduce the radiation from here to here, so radiation factor may be less than 1. A concave phase can radiate onto itself. Planar and convex phases do not radiate onto themselves. Concave and convex effects are automatically considered. So now we'll come to this particular problem. Here we are going to solve several studies, 4 studies. Initially, we are going to solve a static study. Then we'll move to the transient, where we will be applying the heat power from the static study for almost 300 seconds or 5 minutes. Then the next study that we are going to solve will increase the heat power to by 30, up to 30 seconds. Then we are going to shut the heat power and see the effect of the temperature distribution and how it cools down to the room temperature. Then also the last study, we are going to apply the heat power with the help of thermostat. So if the heat ranges or goes beyond certain value, the heat power will be shut off. If it comes below certain value, the heat power will start again. So prior to that, whenever we are dealing with a thermal analysis, we are finding out the temperature distributions and not any kind of thermal stresses or deformation. So in order to define the interface between two components which are transmitting heat, we define the contact as in terms of thermal resistance and not any kind of bonded or no penetration contact. So thermal resistance will obviously restrict the flow of heat transfer. So let's move to Solidworks simulation now. So this is a typical example of the heat power. Okay. So we'll be running 4 conditions. So let's start with the static study where we are not going to vary the heat power with respect to time. So consider this. You can start. Sorry, not this. In the advanced simulation, select thermal. Select OK. So to make sure that it is a static study, right click on this. Go to properties. Select steady state from here. That gives us the final thing. Click OK. So the material is already applied on the component that has been sent to you as well. Now we will define the thermal resistance. So since this will be my heat power thing, heat will be generated in this microchip and it will transfer to the everything else. So we are going to define a thermal resistance between them. So there might be these two components may be connected via glue or some other adhesive. So we need to incorporate that heat transfer condition. So we select contact set here, select thermal resistance. I'll select, or we can simply explode them and apply the. Just go to configuration, change it to exploded view in order to apply the heat resistance in better way. To contact set, select this face, select this face, this face, this face. Total as in the area will be in terms of the Kelvin per watt. If I consider distributed, the area will be considered for heat transfer. So this value is close to 2.857 e to the power -6. Okay, let's collapse this. So now our contact has been established. Now next thing is to apply the heat power. So we'll go to thermal loads. So you can see in terms of static structural problems, we had different loads. That is, they were like forces, pressure, torque, etc. Here the loads are quite different. So we consider heat power. Select the microchip on top. Select this as the 25 watt. So this microchip is developing an internal heat of 25 watt. This is what it indicates. Because, okay. Now, since it is open to atmosphere, we also need to incorporate the effect of convection. So right click on this, click on convection, select all exposed faces, enter the heat transfer coefficient, and let's say the convection coefficient is close to 250. We need to define the ambient temperature, so it will be 300. Click on OK. So since microchip is developing some heat, the heat around this area will be different, obviously. So the convection coefficient is always going to be different. So we'll define one more convection coefficient here. Click on convection. Select, okay, we won't be able to select microchip. So I'll do this, select this, manually. Okay, I think we have selected all the exposed spaces. So heat transfer coefficient will be 100 and bulk ambient temperature is always going to be 300. Click on OK now. Now the next thing is to define the, okay, I think we are done here. So now you can simply mesh it and run it. So I have considered the basic mesh, default mesh that is there, and it is telling me that it is generating a, just I hide the loads in order to see the features better. 447 Kelvin temperature is being, the highest temperature into, observed in the middle part. So I'll move to that part in order to see the results in better way. I'll right click on the result, say select section clipping, select the appropriate plane on which I want to see the result. So I can move this plane forward and backward. So I'll see this area. I'll hide the plane, click OK. So this is the area where it is developing the maximum heat, and the temperature is around 447 Kelvin. We can also change the temperature units, the definition, and select the temperature in units to Celsius. Also, you can see since we have applied the thermal resistance between this, so less heat is being transferred to this area, that is the heat sink. And as we move away from this, obviously heat generation is at the center is almost high, but as we move away, the heat generation reduces. So this was about the static analysis. Now we'll move to the transient one. So I'll simply copy this study. Let's name it transient for 5 minutes. So we want to see the heat transfer at the for the time of 5 minutes. Right click on this, properties, change to transient here. So total time will be 300 seconds, and I want each and I want to plot the results with the increment of 10. So during solving process, it will capture the results after each 10 in seconds. I click OK here. So now when we are going to the transient, we also need to define the initial temperature that was there. So go to thermal loads here, select temperature, select initial temperature, select all exposed phases, and the value will be in degree Celsius as 25. Click on OK here, select run. So you can see the temperature is been applied. So it is open to atmosphere at room temperature. That is what it indicates. And the solution is solving with 10 increments. So each 10 increment consists of 10-second data, and that is why it will take 30 steps to complete, as we are planning solving for 300 seconds. Also, one more thing you can notice, I'll just pause it for a second. In case of thermal analysis, the only degree of freedom is the temperature. So we are getting degrees of freedom 42, 49, 20, and thermal analysis have 1 degree of freedom to them. So that is why whatever the number of nodes, the degrees of freedom equal to that only. So it is not going to vary. In terms of structural analysis, we saw 3 and 6 degrees of freedom in terms of solids as well as shells and beads, respectively. Continue. Okay, so our study has been solved now. So you can see at 1 second, since it was open to atmosphere, I'll just hide this to see the results very better. So it was open to atmosphere. The temperature was very low, so close to -57. Okay, I haven't tried the value. Actually, let's see if something is looking or not. Okay, we are in the right path. So if I animate this, it will plot the results for all the 30 steps. So how you can see the change in seconds here, and how the temperature increasing with that. You can see the maximum temperature going up to 174 and minimum is minus 136 during the solution. You can also plot the results if you want in terms of the graph data. So I have predefined a sensor here. So I'll just select that sensor, go to thermal, right click on results, select graph transient sensors. This is the predefined sensor that is already there. Click on OK, and as you can see in the graph, the temperature is varying from minus 60 to almost 100 degrees Celsius, and it is stabilizing after that. So you can get this data into Excel also if you want to note down all the data. Now we will go and do one more transient analysis. At this time, we will be switching the heat power after 30 seconds. So I'll copy the static study again. Switch off heat power. Click OK. Now we'll simply define. We can also drag and drop the temperature from this into our new study. So no need to create it again. Right click heat power. Define the heat power in terms of the time. So I'll click this icon, click on edit. So this is where I can define my heat power. So this is 0. Okay, one thing is remaining. We need to define the transient study. That is why it was not showing any. Okay, transient data as time up to 300 seconds, time increment by 10. Okay. Now go to the heat power, edit definition. Use the time curve since we want to change our relation with respect to time. 0 to 30, 60, 1, 0. So this indicates the magnitude by which the heat power should be changed. So for 0 seconds, the heat power will be 0. For 30 seconds, it will be maximum, that is 25. And for 60 seconds, it will be 0. And beyond that, it will also be 0. So if I'm 300, it will be 0. So no heat will be generated after 60 seconds. That is what I'm telling. This kind of graph is introduced here. For first 30 seconds, only heating will take place. And we will run this. So as you can see, we got the results. Now we'll simply plot the graph to check the change in heat transfer with respect to. So as you can see here, okay, starting from Celsius, right? Okay, we defined the initial temperature we had to consider from thermal study 1, a transient one, I think. That is why it was showing such a low value. We rerun this study. So the initial temperature was not captured. That is why it was given. Okay. As you can see here, the temperature value has increased to some extent. So let's say it went up to 50 degree, and after 30 seconds, since we have decreased the heat transfer, it has increased, transferred the heat, and then it started to come down. This is what the use of heat power you can use in this way also, by changing it with respect to time and controlling the heat on and off according to your requirement. Now the last thing that we'll be learning about is the thermostat. So I'll be simply copying the study. So just copy this one, no issue with that. As we will also going to apply the heat power. Let's say thermostat. So what exactly thermostat will do is it will control the temperature now. If it goes beyond certain range that we provided, it will start shutting off, and it will get the temperature of the assembly to the some room temperature value or some value. If it goes beyond or lower than the minimum temperature is there, so at that time it will again switch on the heat power and start heating it. This is very helpful in order to incorporate it. So like in many electronic enclosures that we use nowadays, the thermostat is there in order to control the heat, so that in order to avoid the overheating of the components. So one more thing we are going to do is we need to capture more data this time. So I'll say 5. I'll select initial temperatures. Okay. Okay. So I'll select temperature from this one only. Or we can, if we have, since we have defined, no need to consider that as well. Initial temperature, we have selected it. Okay. Only just to, we will capture more data this time, so we will capture the increment of 5 seconds. Everything else looks good. The next thing is to define the thermostat. So go to heat power, edit definition. So here you'll find the option of using the thermostat. We have to close this now. We will be applying the heat power throughout. So I'll simply say heat power will be applied throughout now. The thermostat. So where exactly I want to capture the temperature data from. So I'll select this sensor or this point, or you can select it or not. Go to thermostat, select this, select the data from here. What range you want to change the values to. So let's say I want the change to observe between, let's say, 40 to 60. So if the temperature rises above 60 degrees Celsius, it will shut it off and it will start cooling. Just quickly run this. So I forgot to off this, as we have provided a time curve, that is why it is developing the heat for the first 330 seconds only. So I'll simply say delete these two rows. That will be easier. And not this. For 0, 0, for 301. So the heat power will change linearly. If the value goes up beyond 40, it will shut it off. Run now. Since we have taken the time increment of 5 seconds, it is plotting 60 steps. Okay. So as you can see here, the temperature was rising, it was going up to 60, and when it reached the 60, this particular part, the heat thermostat acted and switch off the heat. Then it came down to, let's say, almost 40. As soon as it crossed 40, the heat power again started, and it again went up. So this is how the thermostat can be useful in your applications in order to incorporate the actual conditions that are there. Okay, so we will begin the second session now.
Yes, sir.
So in this, we will be looking at the optimization part of the designs. So basically what happens is in industries, whenever if we are producing some component or some model or some part on a mass scale, there's a possibility that we can reduce the mass by reducing some material from each and every single component. So suppose, for example, I have a component from which there's a possibility of reducing at least even 30 grams of weight, and if I'm producing that component for almost like in a day, I'm producing almost thousands of those components. 30 by 1000, almost 30 kgs of weight is saved in a day by just doing some modification without compromising with any kind of failure criteria or stress factors or deformation factors or frequency factors. So that is achieved with the help of optimization. So we need to provide certain inputs to the software or solver, and accordingly it will convert your data and give you an optimum shape out of the model that we have initially provided. So with that is what the basic procedure we will be following. So there are few things that we need to define while defining a optimization study. There's objective, there's a design variables, and there are constraints. So objective is what output do I want out of this material, whether I want to minimize the weight, maximize the weight, minimize the thickness, etc. Design variables may be the dimensions that you apply to your model. You can vary those dimensions. I mean, solver will vary those dimensions for you and give you an optimum dimensions out of this. And constraints are the constraint that we provide, a restriction that we provide in order to tell that to software that don't go beyond certain limits. So suppose in terms of stress, so if I want to restrict my values below some certain value, let's say yield strength, so software will consider that while solving and giving an optimum design out of the initial design. So before creating any optimization study, you should create at least one study. It may be static, frequency, or buckling, or thermal. From these studies, you'll get the constraints that you want to apply to your model. So in our particular study, so this is the model that we'll be solving. So this is basically a press used in the industry for punching operation or creating some kinds of dies or holes. So we will be simulating this particular thing, and we will be solving it for static operation and then frequency, and we'll see if considering both of these conditions, do we get an optimum design out of at the end of the simulation. So the first thing we define is the goal. So what exactly I want to achieve out of the simulation. So the goal define the goals of optimization process. So exactly the output that I want from the optimization process. So it may be minimize volume, minimize mass. It may be in terms of the thickness, length, breadth, or any other kind of dimension. So for assemblies with different materials, the optimum design that minimizes volume will be different from the optimum design that minimizes mass. So obviously, mass, even though both of these things are connected, so if you reduce the volume, obviously going to reduce the mass. But if the material is different, or the results may vary accordingly. So you can also consider the buckling load factor, maximize or minimize resonance of the frequency. Then variables are the dimensions that we provide to the software that see you are allowed to make certain changes considering these dimensions, and don't make or don't hamper with any other dimension that are present in the model. So obviously you shouldn't, you should need to make sure the design variable that you are providing shouldn't contradict with any of the relations that are specified in the model. So suppose, for example, in this, you want to optimize the two holes, and after optimization, the one hole is interfering with the small hole, and it is damaging the model. So it shouldn't be like that. So your design variable should be considered in a way that they are not hampering with any other dimension while optimizing. So constraints are basically the restriction that we provide to the solver, that even though you are getting an optimum design out of the study, don't let it cross certain value of stress or certain value of deformation or certain value of frequency. So in this particular, we are going to solve for a static study first, and then we will be applying these goals and restrictions to our model. So quickly move to Solidworks Simulation. Okay. Okay, so this is the bench press that we are going to solve. Just take a look at the inputs for this. So we will be applying the boundary conditions as fixtures on the bottom supports, and applying a load of 22 to 50 newtons on this face. And first we'll solve the static study. With the same fixtures, we will be solving the frequency study. Then we will move to the design optimization part. So first thing to do, start statics simulation. Okay, I'll create a new one because this is the pre-solved study. I'll just quickly create a new one. Okay, so this is the first study. Now we will create a static simulation first, and then we'll move to frequency, and then finally design optimization. So design optimization is it is very famous in the market nowadays, as whenever you go out to buy something, you need to, the first thing you notice, whichever of the component is attractive to look, you go for that for buying purpose. So this is particularly very highly in use nowadays to get the best design out there. So here, first we create static, quickly create the fixtures. I am considering the global bounded contact since all are the solid elements. So no need to define any individual contact to them. Fixtures, then apply load. The value is 22 to 50. Click OK, and simply we'll mesh it a bit so that it won't hamper any of our results, and we get appropriate results when we ask. It takes some time. Okay, it is solved now. So this is the value of 68.4 as the maximum stress we are getting. Okay, and let's see what displacement we are getting here is 0.334 at this end. Okay, so considering the yield strength that I have considered for this model, it's almost 220, and I have a chance to increase the stress beyond to some value in order to reduce some material out of it. So there is a possibility to do that. In the first design itself, if your values going beyond yield point, there's no point in optimizing it as it is already failing. So the next thing is frequency analysis. I'll consider all the parts from here. No connections are required. Pictures from here and mesh from here. So no need to apply external load in this case. Everything else is set. Simply mesh it. Okay, so we are getting first move frequency as 126 hertz. So we need to keep, we are allowed to change the frequency range. So if we tell the software that don't go beyond this frequency and make the desired material changes, it will do it, because our natural frequency is the under root k by m. So obviously, if I am going to increase the mass, the natural frequency is going to be reduced since it is in the denominator. Okay, the next thing is to define, say, design study. So there are two types of the optimization you can perform. One is the topology optimization, one is the design optimization. For the time being, we'll be looking at the design optimization only. If we get time, we'll explore topology. So this is the design optimization window that is open now. So here you can enter the variables, that is the varying dimension which are allowed to change. Here are the constraints, which the things that the stresses or the deformations of the frequency should be below those levels or in those levels, and goals, what exactly is our goal in the final design. So I'll define, let's see what are our inputs. So maximum stress is less than 100. Okay, so these are the design variables that we need to consider. Height of a side plate should vary between 50 and 100 mm. So if I move here, so this is the side plate. So I am allowed to vary this height from or this distance from 100 to 50 to 100 mm. I will be talking about the side plate as this. Okay, no, height as in we are talking about this. So this height should be varied by 50 to 100 mm. Since it is already at 100, it may try to reduce it by up to 50. Cut out of legs vary between 100 to 250. So this cutout, I am telling that it should be allowed to be, this distance should be 100 to 250. So I can reduce some material out of this area. And finally, the length of back plate should vary between 150 to 375. So this is the back plate that we are talking about, and it is at the maximum length. So till 100 mm, I can make the reduction in this particular back plate. These variables I'll be entering now. Let's say add parameter. So name, the first is height of side plate. So I'll name it accordingly. Height of side plate. Model dimension. So the value you need to select from the graphic window. So unit is mm, no comment, I don't want to add any comment. Then the next thing, cut out of legs, cut out of legs, or this distance. So for that I'll select this value. So the value entered here. So basically I'm linking the values that is already present in the model. And the next thing, length of backplate. And this will be this value. So I'll say apply, okay. Just simply drop down from here and select the length of black plate and okay, spelling is wrong here. Okay, no issue. So with range with step, here I get the option whether I want to change the dimension of this particular height of side place, so 100 in some certain range. So first it will try to cover it to 50 and then 100. So only two intervals I'll get. I'll say keep the range whatever you can from 50 to 100. You make the desired changes. Don't apply any step to it. Similarly, length of the back plate, I'll say range. You can either here are three options: range with step, so you get to add the step by which it should vary. Discrete value is the actual values by which it should vary, and range is the range between two values. So the range is 150 to 375. To 375. So I am allowing the software to change these values according to the optimum shape. Again, the range, this should be 100. So I don't want it to be greater than 100. I don't want to add material to this. So that is why I'm telling this 100 to 250. Whereas since it is already at the maximum material level, it will try to reduce to 150 now. So our variables are done. Then we need to define certain constraints. So for constraints, you can define the sensor. You can define the predefined sensor from here, or here's one more option to define it. So I'll say add sensor from simulation data. So whatever the studies we have solved, I need to consider those. I want yes, von Mises will be my considering factor. Unit will be obviously MPa. Then maximum stress should be less than 100 MPa. So my limit, currently my stress value in the static study is 68 MPa. So I have some tolerance to let it allow to move to 100, but don't go beyond 100. That is what I'm telling it. So whatever the model max, you can tell, and across all steps. Okay. So is greater than, is less than. So I'll tell that whatever the maximum value I am getting in the static study that we have solved, that is 68 MPa. You are allowed to increase that up to 100 MPa. That is what I'm telling here. Then the next thing is to define maximum deformation is less than 1 mm. So we'll define one more sensor here. Simulation data, displacement. So maximum deformation in overall model, I want it to be less than 1 mm. Currently it is close to 0.17 something. So there's a plenty of chance to do that. The value in mm. Okay, is less than 1 mm. One more sensor for frequency that I need to add here. Simulation data, frequency. So frequency should be below, should not be more than 80 Hz. Since we are getting the first mode chips at 126, there's a possibility by reducing some material, the frequency master frequency may increase. So I'm on a safer side, I'm keeping it the limit as 80 mm. is more than 80 Hz. So minimum frequency should be, in this case, 80. Now one more addition I can make here is I don't want the vertical height to change in this matter. So I'll add one more sensor, add sensor, simulation data, displacement. So I don't want y direction displacement to change. Let's say mm. Maximum over selected entities is what I'm going to select. Select this edge, as I don't want it to move beyond certain value. Only let's say what is the current value of this plate now. So it's 25.4, almost 1 inch plate. So I'll say, okay, allow it to move till 5 mm, but don't go beyond that. So I'll click on OK, and is less than 5 mm. So here you can define if you are having multiple studies, from which studies which data to consider. So accordingly, it will consider the data. Since we have only static and frequency, by default, it has considered the for stresses and displacement data from static study, for frequency related data from frequency study. Simple as that. Okay. The next thing is to define the goal. So our objective is to minimize the mass. So of the whole assembly mass, whether I can reduce mass, volume, or center of mass in x, y, and z, that is CG along x, y, and z direction. So I'll say create center, reduce mass, and say minimize. I can also change it to close to, so I will have to give a specific value to it. But currently I don't know what exactly the optimum shape might look like, so I'll say minimize. Then our setup is done here. Next thing is to do is run the simulation. So it is creating, so it has from the calculation, it has judged that there might be 15 scenarios. So out of those 15 scenarios, it will give us some results. In the graphic window also, you can see the changes happening once the changes start happening. It takes almost 10 to 15 minutes to solve. So here you can see it is creating number of iterations, changing the dimension that we have told it to change. At the same time, here you can see the value was earlier 100, now it is changed to 175. So it is running the first iteration, and it is checking whether it is satisfying the stress, displacement, and frequency criteria that we have fed it. So it has reduced this height length now on its own, considering the safety criteria. So almost 6 scenarios have been solved. So it is bit time-consuming process, as it is running multiple static studies and frequency studies now. Here you can see the frequency study solving now. So it is generating data at each and every iteration. Since we are making the changes in the dimensions of the design, that is why for each and every iteration it will solve individual static and frequency study. So now you can see it is solving static study for the 7th iteration. So if you have any doubts related to this, you can ask, because it may take some time to get the results.
So actually I joined in a bit late. Can you just say that how you have started making this table means result?
Yes, okay. Okay, so from which point you have joined? Was the study already solving, or prior to that?
A little prior to that, while you were making the table.
Okay. So basically what we have done is we have first solved the static and frequency study. We have followed the step that I have told you in the previous few sessions. So we have solved these two studies. That is the step 1. The next thing, we have considered these dimensions as our design variable. So I'm telling the software key, you are allowed to vary these particular dimensions which are highlighted in the graphic window. So based on this dimension, give me an optimum shape out of it. Don't make changes to any other dimensions, only the dimensions which are mentioned in the graphical window. So this is the first step that we have done. We have captured all the dimensions from the graphical window. The next thing we have done is provided the constraint to it. So we have told the software that I'm getting the value of stress in the static study that we have solved. We were getting the value of stress as 68 MPa, and our frequency first mode shift was observed at 126 hertz. So from these particular two data, I'm telling the software, I am getting my first value as 68 MPa. So you are allowed to make changes till the stress value reaches 100 MPa, but don't go beyond that. This is the first input I have provided. Then the second input was, I'm telling the software that the deformation was coming as 0.175 something. Here you can see the actual value. Yeah, so displacement or the deformation was coming as 0.334. So I'm telling that you are allowed to increase the displacement, but don't go beyond 1 mm. And the frequency is 126 hertz. So I'm telling that get the mode shift or frequency. You are allowed to, since you are reducing the material, you are allowed to get the frequency greater than 80 hertz. Don't go below this. These are the inputs that we have provided, and the final goal of this whole procedure is to minimize the mass. So finally, we have defined the mass criteria for it. So you
Means
doing
it will
all this.
Means it will automatically optimize the mass.
Yes. So currently, since it is solving, I am unable to move the sliders here, but you can see one more column with the weight of the component. So we will, after doing this, we will compare the initial and the optimal weight. So it is currently solving all the iterations here. So you can see the first iteration, second, third, fourth. So those iterations which are in red colors, so those have failed certain criteria. So suppose the second iteration failed to go or consider the frequency beyond 80 hertz. So that is why it is failed. The second iteration, here you can see the stress value is 133, which is above our criteria of 100 MPa. Similarly for the third. So accordingly, it is running the study now. It is changing the dimensions. It is then rerunning the study and getting the optimum results out of it.
Oh, okay, sir. And actually, from where you have or which option you have started making this table?
Okay, the design study. In the new study, in the simulation tab, when you click on new study, there's an option to create design study. So I'll show you once it is done. Since it is solving, I'm unable to do anything right now.
Okay.
I'll show you
I
that.
got it.
In the meantime, is Shibendu sir here? Roy sir? Is he here?
No, I guess.
Okay. So I just wanted to send you a training form. on which I require your signature for our internal documentation. So I'll just mail you all with CC to him, and or you can just any of you go and make a printout of it after completion of this training and send it back to me with a scanned copy and stamp of your organization or institute. So I will just mail you a form after completion of this training. Kindly just fill the form and send it back to me. Okay, so this is the optimum design it has given us. So you can see, just make it big. Okay. Okay, here. So you can see the initial mass was, let's change the unit. Okay, let's keep them as it is. Otherwise, we'll also. Okay, so here the initial mass was almost 60 kgs, and it has given the mass hasn't changed much bit, but at the same time, it has given reduced certain dimensions, and it has given us this optimum design. So earlier, what I was saying, I'll plot the initial step. So this is the initial design of our structure, and this is the final design. So at certain intervals, it has reduced the mass of this. The mass variation is not significant, as you can see, but if you see the size of this plate, it has been reduced. So overall, if you go and build the mass, you can save the material on this particular plate while manufacturing it. Also, it has created certain iterations which haven't actually which have actually qualified but the mass is increased in all of those iterations. So you can see, if I consider iteration 1, it hasn't made any such changes. It has been able to reduce the stress. The deformation is not much significant. The frequency is increased, but at the same time, it has increased the mass. So we shouldn't go for this. Uh, Out of the 15 iterations that it has calculated, it has given us this one, that is as optimum one. So if you want to go for manufacturing, we should go for this, and it is completely safe to use. And the stress value is almost 98.92, which is below our stress value 100 MPa. Displacement is 0.52, which is less than 1 mm. Frequency is 81 hertz, which is greater than 80 hertz, but at the same time, it is less than the natural frequency. So obviously, we can accept this. This particular displacement that we had defined is restricted to 0.15. But at the same time, there's not much significant change in mass. In case of all other studies, it has been able to increase the mass or not able to satisfy any of the criteria. So that is why I can say that, or the software has calculated that this is the optimum design. So whenever I consider as the optimum design, whichever design I choose, so it will automatically make the diametrical changes in the graphical window. So suppose I'll go for the optimum design, and if I want to check the stresses and deformations occurring in it, I'll simply go to static study. So this study has been updated with the new dimensions. All I want to do is simply update all components. Let's see if we can get the results. Okay, so results are updated. You can see the stresses and deformation. Okay, the results are not updated actually. I thought it's gone. So just rerun it, you will get the desired stresses and deformations related to it. What was it saying? No element group is defined. Okay, so it is saying that the mesh is missing out of this. Simply remesh it. So now you can see earlier I had moved this slider to the extreme right side, but since the geometry has been changed a bit, that is why it has given the mesh cursor to this range prior to. So I'll show you. So based on the geometrical dimensions that are present currently, it will apply it won't change the mesh element size. Only the range of element size has been increased now. So since much of the material is removed in this area, we are allowed to mesh it with more finer elements. If I click mesh, I have the pictures. Yes, the pictures are defined properly. We rerun it, we'll get the desired stresses and deformations for this particular design scenario. So this is where I'm getting the stress value of 98.574. If I want to compare it with where I was getting the stress value for the original design, I'll simply select go to design study, select initial from here, go to static study again, and rerun it. So you can see the stress values at the same location, but the value is quite low as compared to the optimum design. So this is how you can use the design optimization for the sake of your understanding, or whenever if you are doing your projects in the final year, you can, if you are manufacturing something and you want to provide a better or optimum solution, at that time you can use this study. So first thing is to provide static data, then go for the design study and make the desired changes, or get the number of alternatives which can be manufactured with this particular design. And I think it will be really impressive to show this kind of things at your level also. Then the next thing we can do is
Yes, sir. It's a 1 minute, sir.
Bilkul.
I asked you, I requested you to just show
Yes,
that
yes,
how
sorry.
to.
Yes, sorry. Just I'll show you again. So go to, in the simulation tab, go to new study. So in the design inside, there are two options. There's a topology study, there's a design study. This is what we have solved. So topology study deals with the shape optimization of particular component. So it is actually a very time consuming study to solve. So currently that is why we won't be able to look at this. But we have seen the design study. Click on this, click OK. So you get to apply the options here. In the variables, you can define the
Now can
different.
I add the variables here?
Yes, you get the apply the dimension in the constraints. You get to apply whatever the constraints you want to apply. So it may be displacement frequency or stresses. And in the goal, what exactly is your goal? So I have defined the goal as to reduce the mass. So I've selected the mass as my sensor and minimize it. Okay, got it?
Thank you.
Hello?
Yes, I got
Hello?
it. Thank you.
Yes. Okay, shall we move forward then? Anyone has
Yes,
any
sir.
doubt related to this? Okay, otherwise we'll move forward. I'll be back in 2 minutes. Okay, so we are done with design study now.
How to
Yes.
capture the dimensions? Sir, how to
Okay.
capture the dimensions?
Yes, I'll show you. Okay, in the design study, if you click on any of the add parameters, you'll get an option to enter the name. So simply, let's just say I'll delete this first and again add it. Suppose I want to capture the let's say thickness of a certain component. Net, annotations. So simply just go add parameter here. Type what parameter that you want to consider. So suppose I want to again height of side plate, let's say a side plate simply. So in the model dimension here, you just need to select. If I want to, let's say, vary this dimension, let's say width of the side plate, width of top plate, sorry, top plate of press. So simply type in the name and simply select that dimension. Okay, since it is driven dimension, it cannot be defined. You need to have the driving dimensions to capture them. So these are the driving dimensions which are free to move or free to change. Maybe this dimensions is controlled by some other parameter. That is why I'm unable to capture this.
Okay, sir.
Okay.
Okay, sir. I got it. I just wanted to know the process. It's okay.
Yes, sir. Yes, it's very simple.
Thank you, sir.
Okay, so everything clear related to design optimization? Do you guys have any more queries? Okay. So now we'll move to the next part. That is okay. So now we'll be learning about the non-linear analysis. So this is the first time we'll be checking this out. Okay. So what linear static analysis assumes is that the material is linear. That is, if you apply a load of 100 Newton and you are getting displacement of, let's say, 2 mm, after application of load of, let's say, 200 mm, you are going to get a displacement of 4 mm. So this is what the linear static analysis first assumption. The second is till you apply the load, the model will deform. After removal of the load, the model will regain its original position. And finally, the loads are not changing with any direction, or the loads are steady. They are not applied rapidly. So these are the basic assumptions of linear static analysis. So now when we move to nonlinear analysis, so basically what happens, I'll explain this to you with the help of some work here. Okay, so imagine this as my single cantilever beam, and I am applying the load. Let's say I'm applying some load of F on this, and it is fixed at this end. So this end is fixed. So this is my simple cantilever beam. If I'm applying a load, let's say F, and if it is in the linear elastic zone, what will happen is my load that is being developed here, F, it's try notepad. So if we are in the linear elastic zone, the one that I've shown you on the stress strain curve, so F that I am applying will be equal to stiffness matrix times the deformation. So it after the application of load, let's say it is deforming like this after the application of load. So this displacement is around, let's say, x or x naught. So during this process, my force or my stiffness matrix, we will assume this as the K0. So my stiffness is at initial position. As soon as I remove the load, this structure will gain its original shape, and there are no residuals present. So what happens if I increase this load very much? So let's say the load that I am applying is like very big. So earlier I was applying the load with the magnitude of F. Now I am changing it to, let's say, 1000 F or 100 F. So what happens at this point? There are some plastic deformation. The material will try to go into the plastic zone. So this we can say as plastic zone. So what exactly happens now? My force, whatever is going to happen, the thing that is happening is, it is initially it was vertical in this direction. As soon as my beam started to bend, it changed its direction, and now the load direction will be this way. More the bending will occur. So suppose more the bending, the load direction will change accordingly. So now this will be my load direction. So at each and every point, what happens is, initially my stiffness was k0 and displacement was x. Now when the material enters the plastic zone, my material will have certain the change in some stiffness. So new stiffness will be k1 times of x, and this will be my f1. So similarly, if I go on increasing the load, obviously my load magnitude is changing. At the same time, my stiffness of the material is also changing. So earlier in the linear static analysis, what we did is we kept the stiffness of the material constant throughout the analysis. That is why after the removal of load, it was regaining its original shape. But now some plastic deformation is observed in the model. Some permanent deformation is observed. That is why after application of each and every loading condition, the stiffness of the model is, or the component is changing, which is resulting in the non-linear behavior of the component. So basically there are three, this particular behavior we known as the non-linear. So the differential, basically it comes from the differential equation. I think you must all have learned in the mathematics that there are two types of differential equation. One is the linear, one is the non-linear. And if there's a multiplication present of the dependent and independent variables, we call it as the non-linear differential equation. So in the backhand, this is what happening. The mathematical equations required for solving these particular types of elements or these particular types of materials which are entering in the plastic zone, the type is the mathematical equations are turning into a non-linear type. That is what exactly happens. So there are basically three types of non-linearities that are present. One is the geometric, one is the material, and one is the contact. So the non-linear is a totally different module, and you need to have some dedicated time allotted to learn the things or different types of analysis. But since due to the time constraint, we'll be simply seeing the introduction related to this. So if you are dealing with suppose very large moment at the cantilever end, or you are dealing with some rubber like material which is having Poisson ratio close to 0.5. So we all know that when the material's Poisson ratio is close to 0.5, they may behave like totally elastic in nature. So there might be very less plasticity. So in order to, but they at the same time they will be hyper elastic. So the phenomena captured by the metals is not equivalent to the phenomena captured by the rubbers or material like those having high hyper elastic in nature. So basically non-linear, so there are, in case of material elasticity, so we are seeing that first we'll see the material, then geometric and contact. There are three types of non-linearities. So in case of material non-linearities, there is a non-linear elasticity, suppose like rubber-like material, for example, or if you are trying to blow a balloon, so as soon as the pressure inside the balloon increases, the balloon size will increase, and also it will start stretching. At the same time, when you are applying the pressure, at each and every blow, the pressure direction is going to change inside the balloon. So that also comes under the material non-linearity that is observed. So plasticity is when during the loading condition, as I've shown you in the cantilever problem, if you increase the load is supposed to change its direction according to the change in deformation or change in the cantilevered shape. So that comes under the plasticity, because there's some permanent strain or permanent deformation that is occurring in the material. So we are dealing with, basically, if I draw a stress strain curve here. So this will be your elastic zone. After some point, this will be your yield point. This will be your maximum yield point. So not like this. So this will be your maximum yield point. And after crossing this yield point, there might be some permanent deformation that is happening in your model. So the model will not be able to go to its, oh, sorry, it has to be corrected here. Here. So this is the permanent deformation that is occurring in your model, and the model is unable to regain its original shape. This is the permanent deformation that is observed in the model after entering the plastic zone. So that kind of phenomenon is captured with the help of nonlinear analysis. And as I've already told you, hyperelastic materials like polymers, rubbers, gasket material, when strain reaches significant value, so tens to hundreds of percent. So if the change in strain goes beyond this value, like 10% of the strain has been increased in observed in the model, or creep or plasticity. So creep is a specific repetitive loading condition that occurs in most of the metals, mostly in the boilers. Due to the continuous temperature loading, there are some pit formation is happening, or to check the viscoelasticity of certain components, we can use the non-linear analysis. So this was about the material non-linearity. Then there's a boundary non-linearity. So it is totally related to context that we define in a structure. If they are how they are interacting with each other. So yesterday I've shown you to the example of the block to define the nonlinear analysis. And while showing that, if we would have solved it, since the two components were the small block was sliding on the plate, this type of analysis is usually performed with the help of nonlinear analysis, and the material behavior is more captured in more detailed way. So whatever the contact related issues are there, specifically with the no penetration contact, those are solved with the help of boundary nonlinearities. Linear spring, if so, it obeys the Hooke's law. There's after applying the force F, there is no permanent deformation, and when we release this force, it will regain its original position. But if the spring is non-linear in nature, that is beyond certain point, there is a possibility of some permanent deformation occurrence. The spring won't regain its original shape or size, and some permanent deformation will be left there. So these types of problems should be solved using the nonlinear analysis. So this is what I have explained with the help of the figure. So the load will be applied in small number of incremental steps, and during the change in each loading condition, the stiffness is going to change as the deformation is changing and loading direction is changing. So these things we saw with the help of the cantilevered example. So here you can see that in case of linear problems, K is independent on U and F, whereas in nonlinear problems, since some permanent strain is observed, the stiffness is changing, and the U, that is displacement, and the force are totally dependent on the stiffness of the component. So geometric nonlinearities are, as I have already mentioned, that these are important to capture when the parts deform very much, maybe in the plastic zone, maybe beyond that point. So if you can imagine a buckle of your bags, where there's a female part and there's a male part, and you push one into another. So the snap action that needs to be captured, we cannot capture that with the help of the static analysis, because there's a continuous change in the motion. Also, the material required to apply is plastic in nature. So we need to capture this with this phenomena, particularly with the help of nonlinear analysis. So we'll be seeing a simple example of this hose clamp. So we'll be applying one fixture at end, and applying a rotational load at other end. and we'll be seeing the results with the help of static, and then we'll compare it with the nonlinear studies. This is a simple example of hose clamp. So the actual behavior should be like, I'm fixing it at one end, and this end I'm applying a rotational motion, so that it should regain its or it should deform in such a way that we are getting the hose clamp that we see in real life. So this is what the hose clamps look like. So you bend it in certain way and fix the two ends with the help of a screw with each other. Simulation studies. Now we will select the in case of static, not static, sorry, non-linear. So there are two studies present here. One is the static study. So in the that means that we won't be considering the time domain now. Only load will be applied in number of steps. Now there is also dynamic study. So here the loads will be a function of time. So whatever the change is happening with respect to time, that will be captured. So in real life, all the phenomena that we observe, those are the dynamic in nature. So if you want to simulate real life problems, you should go for the dynamic, but static will give you an idea about how things are happening. So this is okay. First we'll solve with the static study, then we'll move to the nonlinear. Okay. The material is already been applied. Since single part, no fixtures are no connections are required. We'll apply fixed geometry fixture. So one more thing you can observe, since it is a I think it is made, yeah. Since it is a we have converted into sheet metal part. So while importing into SolidWorks simulation, it has directly converted into sheet metal part, and whatever the mesh will be applied, it will be shell mesh. So this is one advantage. So whether you are using weld bends, if you are using weld bends in your assembly, that is the structural members. When you import them to SolidWorks simulation, those will be directly converted into beam elements. If you are using the sheet metal from the SolidWorks CAD, those will be directly converted into shell elements. So no need to define like the procedure that we followed in the morning, that is rightly defined by selected faces, define shell by selected faces and apply the thickness. It will directly consider the data from the CAD itself. Now the next thing is fixed geometry, fix this edge. So in case of shell elements or sheet metal parts, you need to consider the thickness, as only one of the surface will be there for a simulation purpose. Then I'll apply some prescribed displacement. So I want this part, I'll tell that with reference to, let's say, I'll apply it on a flat face, no issue. On this flat, select this flat face. So I don't want it to move in X direction. So I'll simply restrict planar motion. So it won't actually, when it will try to bend, it is supposed to move in the X direction. So we cannot constrain this, but I don't want it to wobble in the XY plane. So I don't want the movement to happen like this in the XY plane or along Y direction. So I'll restrict that by saying along direction 2. So you don't let it move in this direction. Now we will apply some rotational constraints to it. So I want it to bend at this particular fixed support and come to this hose clamp that we see in real life, or get the shape of the hose clamp that we see in real life. So then rotational direction 1. So along rotational direction 1 x, as in it won't twist in this direction x. When we consider with global coordinate system, our direction 1 is x, direction 2 is y, and direction 3 is normal to face. So whatever the face we are selecting, the movement normal to it will be considered. So now we are applying the rotational constraint. So you can see, I'll highlight the symbol a bit. Yes, 200. So you can see the rotational direction. It is having some bolt-like structure. So the top or the rotational direction will be indicated. You can use the thumb rule to understand this. So your thumb will be in the pointing direction towards where it is going, and your right hand thumb rule and your curved fingers will indicate the rotational direction that we are restricting. So this will be the first, then second direction 2. So along this direction in the y, along y, I want it to rotate and come to this position. So total, I want it to rotate by 360 degree. So what here the option is to apply by radian. So you can convert the 360 degree to radians. It's coming close to 6.27. And the next thing is, okay, I think this will be enough. Normal to face. If this is the face I'm selecting, whether I want it to rotate, no, like this in this plane. I'll say X. Yeah. So already we are considering normal to direction 1, restricting this. So no need to define, or we can define any of these. So I'll remove this. I'll quickly solve it. So during the solving, it will, yes. So it is telling me that the excessive displacements are observed in your model. So whether you should go for large displacement where load will be in multiple number of steps. Currently, the load is being applied at the single step. That is why it is unable to solve it, or the results we may get may not be proper. So I'll say no, plot the results. First we'll see the results out of this, then we'll rerun it and check what kind of changes we can make. So I'll say no. So it is set to certain deformation scale. If I convert it to true scale here, so this kind of behavior it is giving. Since we are solving it in the linear static analysis, the load direction is not changing as the simulation proceeds. So this is not the proper behavior that we want to capture. So now we'll try to figure out one more option from this, that we will apply the load. We will tell the software to apply the load in number of steps. So to do that, the first thing you can do is either change to nonlinear analysis, or you can apply the load in number of steps. So let's say if I click on large displacement here, so in static analysis itself, the solver will consider the large displacement of this particular structure. So it will apply the load in number of steps. So whatever the deformation is observed, the load direction will change accordingly. This is what we are telling. So let's see what results we get with this. So load is now being applied in number of steps. Here you can see. Initially, when we were solving the static analysis without in small displacement, the load was applied in single step. That is why it was going in downward direction only. It was unable to change the loading direction. That is why it was unable to rotate. Are you guys clear about the theory related to nonlinear analysis? Hello?
Yes,
Simply
sir. Yes,
typing
sir.
it.
Theory is clear. Yeah,
Okay, okay.
theory is clear.
So we haven't moved to actually nonlinear as of now. We are simply in the static, linear static analysis. We'll move to the nonlinear once after getting these results. So we'll see the behavior after this, what exactly the behavior is we are getting. So each and every step, the load direction is changing. Load is incrementing, not exactly incrementing. Load direction is changing in each and every step. That is why it is taking much more time to solve. Earlier, the direction was only in the one direction, so we were unable to capture the proper behavior. Okay, so now you can see we have captured the proper behavior, but it is interfering. So if I animate this, so it is going, the animation is not properly captured here. So it is unable to plot the proper behavior or proper animation in this scenario, as we are only in the linear static analysis, but the behavior is totally plastic in nature. Because when we bend the hose clamp, it is totally going to, there is some plastic deformation or permanent deformation that is going to be there. So it is not capturing, not able to capture the proper behavior. If you see the stress plot, you can see it is moving in this direction only. It is not bending like as we were expecting. So let's check if we have applied the proper boundary conditions. So in this, we are allowing it to, we don't allow it, not allowing it to move in this. Normal to face, so we are not allowing it to rotate in this also. Normal to face movement. So let's see if we are clicking this, we are able to solve this study or not. Along face direction 1. Yeah, I forgot to do this. Yeah. Let's see if we are getting some different results or not. I'm sorry. Have you all received the recording link that I've sent in the morning of yesterday's session?
Yes, sir. We received it.
Okay, okay. So all you guys need to go to the college to attend the classes, or classes are still going online?
No, sir, actually we are having our online classes now.
Okay.
We don't know when our college will open.
Okay.
Reopen. We are at our home.
Okay. 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 So the behavior is not properly captured in this case also. So now we will move to the nonlinear. Even though end product that we are expecting it is there, but you can see there's small interference happening at the end, and this is not what we need to get as the final result. So now I will, keeping all the parameters as the same, I will copy this study and change to nonlinear from here, nonlinear static. Click on OK. So in nonlinear static, I'm keeping all the other parameters as the same. The one thing that you can access from here is you get to enter the start and end time. But since we are dealing with the static only, so whatever the time increment that we are allowing, that will be considered as the pseudo time, and this time increment will be applied in terms of the loading steps. So if I'm considering start to an end time as 1 second, so this is not the actual time that I'm entering here. These are the pseudo steps considered for the loading increment purpose. So there are two options: automatic increment and fixed increment. So what kind of increment do I need to capture from 0 to 1 second? So I'll keep first, let's say automatic auto stepping. So initial time increment. So from moving to 0 to 0 0.01, actually now from 1 to 0. So now if I'm considering that that initial time increment as 0.01, maximum time of each and every step is 0.1. So I can divide my number of steps as 0.1, 1 divided. So in total 10 steps will be, this problem will be solved in 10 number of steps, and each increment will be of, let's say first initially this will be the increment, and then maximum increment will be this. So at each and every step, the software or the solver will try to converge my results. If I don't, if I am unable to converge, it will change this stepping time, or it will reduce the stepping time, and it can go up to 1 e raised to 0.8 minus 0.8. So suppose in the first step, which is having maximum time step as 0.1. So let's say I've begun with 0. Now the second step is going on 0.1. At this step, I am unable to converge my results. So the solver will try to reduce this step now. So what it will do during the next step, which is supposed to be 0.2, but since we are not getting the result, the next step will be 0.01. So 0.11 time it will try to again solve for the convergence. If it is unable to attain convergence, it will again reduce the step. So it will go to 0. Let's say 001. So on and so forth. So up to like 5 adjustments it can make to reach this value or to converge the results. So till now we have made the 3 adjustments. If it is not converging those adjustments, it will stop the analysis and tell that some numerical difficulties are observed. If it can attain, let's say after third iteration or third adjustment, it is able to converge, then the next step will obviously be 0.1. So we will be able to capture 0.211 time step. So since we are in the static analysis, this time increments are only for the purpose of loading condition, application of loading conditions, and this may not be the actual time steps. So we call them as the pseudo time steps in case of nonlinear static analysis. When we move to the nonlinear dynamic analysis, so their actual time increment is considered. So real time, whatever operations or whatever loadings are happening in the real time, those are applied in those cases. So obviously when we shift to nonlinear analysis, it will use the large displacement formulation. In static also we got the option, but we were unable to get the proper motion involved in this. So let's see if I am unable to converge my results with this time step, or do I need to make any further changes. Quickly run this. So now while solving the nonlinear analysis, you can see the deformation that is happening. And here you can see the current solution time step that it is solving for. So current step size and total solution time. So almost 25% is 30% is completed. Also in the legend, you can see the permanent deformation is going beyond some value. Earlier it was increasing, now it is again decreasing as we move in the number of steps. As this, there's a concept of strain hardening while making the plastic deformation. So the concept is quite difficult to understand at this phase. Once you move ahead in the maybe next year, or when you are working on some plastic models, at that time the concept of strain hardening will be easier for you to understand. Okay, so now we are getting the proper behavior. So this is kind of behavior that I want to see while deforming. If I animate this now, you can see how it is deforming due to the loading condition that we have applied. So you can see during each and every step, the load direction is changing. That is why it is behaving like this, and we are getting this kind of behavior. So whenever the problem requires change in load direction, you should go for the nonlinear analysis. So this was about the introduction to nonlinear analysis. The time required to cover the whole aspects of nonlinearities is a bit much. So I think I won't be able to capture that or cover that in today's session. But in the future, if you guys require the training related to specifically nonlinear analysis, whether it may be static or dynamic, I'll be able to provide it. So considering today's time frame, we have to move on. So if you have any doubts related to this, kindly ask me now. Otherwise, we'll move forward.
Sir, how to incorporate a large displacement?
Okay, I'll show you. So in case of large displacement will be incorporated in case of static analysis only. By nonlinear, by default, it is checked on. So in case of static, go to the title of your analysis, right click on it, go to properties, and here you get the option to whether to incorporate this or not. If you click this, it will consider the large displacement and the loads will be applied in number of steps. If you uncheck this, the loads will be similar. Okay.
You have to right click it and okay.
Yes. Select the here from the properties. You can select whatever.
Okay, sir, I got it.
Okay. Okay. This was about the large displacement analysis. So, okay, one more thing. There are two options I have already solved with the help of auto time stepping. When we go with the fixed time increment, the increment that in case of auto time stepping, what happens is the results won't vary, but auto time stepping allows the solver to select the time step according to its requirement. In case of if I select this fix, it has to go by this fixed time frame only. So if my first time step is coming at 0.1, next has to come at 0.2, even though the solver is converging or not. If it doesn't converge, it will fail the analysis. But in this case, if it fails to converge in first step, it will reduce the time step and again try to converge it. So this is one more benefit of this. Okay. So these are the results that we saw. Load at the end of simulation. Okay. So this is simply the time curve that has been introduced. I'll show that also. So when we go to non-linear analysis, whatever the loads that we have defined, you get to apply the loads in terms of the time curve also. So if even though it's linear, if I change to curve, it will show me the basic linear behavior of the loading. If I want, I can change the magnitude according to. So suppose I want 0.5 as my first movement, 1 second, and till 0.5, I want my magnitude to reach, let's say, 75% of its value, and at the end of one final. So this will be my loading curve, and according to this loading curve, the loads will be applied to your model. Okay. Okay. So I think we have covered almost the things that we can use in case of structural analysis or simulations. Now we will move to the kinematics part. So yesterday, Shubhendu sir was also asking, and he was concerned about whether I will be taking that part also. So we will first go through the motion analysis basics, what exactly is there. Then I'll show you one example related to it, and maybe at the end, if sir is here, we will try to solve the model that you have shared with me, the slider crank model, and we will try to import it into simulation and see if we are getting any results or what kind of results we are getting out of it. So basically, motion is the study of moving systems or mechanisms. Prior to simulation, we perform motion analysis in order to check how our mechanisms are behaving, if they are interfering with each other, if they are coming in contact with each other, how exactly the behavior is. So we don't perform motion analysis for single parts. It is only related to the assemblies, obviously. So motion of a system is determined by the mates connecting parts. So in case of simulation, the mates, whatever mates we give in SolidWorks CAD, those are of not much importance as they are not considered. But in case of motion analysis, you need to be perfect with your mates, and you need to apply the proper boundary condition related to mates. So we consider the mass and inertia properties of the component. So obviously, with whatever mass, whatever the material we are applying, depending on the mass of the material and the inertial properties, that is the acceleration and velocities that are generating in the model, those are considered. Forces applied to the system, we can move the components with the help of motors and actuators. I'll show you when we move to the SolidWorks window. And we can also incorporate the time curves, time frame, how different components are moving with respect to time. There are two types of mechanism types. One is the kinematic system, and then is the dynamic system. So in case of kinematic system, the movement of parts under enforced or constant motion only. So fully controlled and only one possible motion results with respect to force and mass. 0 degrees of freedom in case of kinematics. So I'll define certain, suppose if this is the mechanism that I'm dealing with, I'll be applying a single load at the top face, telling it to just move upward and downward. It won't affect any of, or it won't try to move in any other direction. Whereas in dynamic components, the parts are free to move subject to the force that we are applying. So suppose if I'm applying the force from, let's say, this direction and applying the motor in the vertical direction, so it may wobble while moving upwards. So these kinds of things we can capture. So in case of dynamic system, they may have infinite number of results depending on the forces, and they may have greater than 0 degrees of freedom, since the forces are defining the motion related to dynamic system. But in this case, only the linear actuators are defining the motion. So let's go through some basics. So Newton's first law is there. Everybody we all know this first law. The body continues to be in state of rest or uniform motion until and unless any unbalanced force is applied on it. Then there's a conservation of momentum that is also used. So summation of F, all the forces acting in a body, is the rate of change of momentum with respect to time. So we can also write it as P is the momentum, which is equal to mv, and mass being constant throughout the system. Since we are considering the rigid bodies, we can take the mass outwards of the differential, and it will be dv by dt, that is equal to acceleration. And so similarly for the angular momentum, the sum of moments acting in the body is the rate of change of angular momentum about time. Then rigid bodies, as I've told you, okay, we haven't covered this, but rigid bodies will have 6 degrees of freedom always. There is no concept of solid shell beams in this particular scenario. your body is allowed to move in 3 translational and 3 rotational degrees of freedom. So when we fix a body, all degrees of freedom are fixed. Okay, so we'll be seeing this simple example of the car jack, which is very considering the weight of almost 8,900 Newton of a car. So in this, we are not going to consider any kind of stresses or deformation, only the behavior. The output that we require out of this is, if I am applying a motor, what should be the rating of the motor that I need to select for considering for lifting some car, or what kind of power of the motor should be. These parameters like this can be found out with the help of this. So one more thing to discuss before this. So, okay, I'll explain to you when we are solving that particular car jack problem. Okay, by default I have so this is my simple car jack problem. This car jack, this will be lifting point of the car, and from here at this end I'll be applying the motor. I have fixed each and every with the hinge mates, whatever the rotation is going to be there. So you need to make sure that you are applying the proper mates, whatever the motion you are expecting out of your mechanism. Prior to going in detail, you must apply the proper mates to them. Motion study. So you need to on SolidWorks Motion from here. We are going to find the motor torque and motor power that is required to lift certain components, some parts like car. These are the basic window of SolidWorks Motion. From here, you can define the time for what time frame which load should be applied. So here are 3 options available. There's an animation, there's a basic motion, and there's a motion analysis. So animation will basically give you a basic illustration of it is basically for the illustration purpose. No loads or reaction forces can be calculated with this. There might be a possibility that if you select animation and if there are some interferences, it will consider those interferences as well and give you a basic animation of your movement. Then basic motion, it is the animation basically where gravity, mass, and collision are applied to the parts in the model. So if you want to incorporate gravity, which you can do from here, there's an option for this, or some mass is allotted to this. If you want to incorporate these things, you can go for basic motion. And motion analysis is the actual kinematic study which considers the complete rigid body simulation environment used to obtain numerically accurate physics-based data and animations. So whatever the actual physics that is going to happen or that is going to be considered while this motion purpose, that can be captured with the help of motion analysis. So basically this is the kinematic study or dynamic study that we can use to get the proper physics related to any kind of mechanism. So now we will simply define a motor at this end. So this is the lifting point. It will, when it will rotate, this car the car will be mounted on this. So this point will try to go upwards. So simply define a motor. I think you have used the motion analysis because the model that I have received in today morning.
Yes, we did this motion analysis before.
Yes. I think so. You must be aware about it.
Yeah, motor. No.
Okay.
And with the
So
side tracking mechanism, which we have sent you, there also we have used this motion
yes,
analysis
that is
using
why
motor.
yes, I observed that. Okay. So here you get to apply different parameters, what kind of motor you want to apply. So if it's constant speed, it will rotate at 100 RPM. If it's a certain distance, so you can tell the software to what distance it should rotate. So if I'm applying a motor and saying the distance to be 90 degree in 0 to 5 seconds, so it will rotate only by 90 degrees. Similarly, for the linear actuator as well, if you are defining the distance, it will go a linear movement in that direction. Then there's oscillatory motion. So if you want some motor to imitate the oscillatory movement, you can do that. Then these three are some advanced things. If you want to define segments, so if I click on segments, it will give me so if I want to define my motor with the help of some functions, it may be displacement and time, and I can define them. So suppose if I enter here, let's say from 0 to 1 second, I want my motor to, let's say, rotate by 30 degrees. From this to 1 to 2 seconds, let's say it's 90 degrees. So I'm increasing the angular velocity here. Then after 2 to 3 seconds, let's say 150 degrees. So this kind of change in the motor movement or rotation you can capture with the help of this segment. Here you get to define what kind of segments you want to plot. So there are a number of segments available. So if you are plotting the cubic, your curve will look like this. If you change the function, quarter sine rule, the curve will shift. If you are considering linear, the curve will be in linear format. So you can see the from 0 to 1 second, it's the behavior is linear. If you change this to, let's say, half cosine, the curve behavior will change. Accordingly, according to your need, you can apply the properties. Then there's a data point. So basically, at what time, what value I need. This is simple as that. So there are three possibilities: cubic spline, linear, and Akima spline. So in order to fit most of the data in your analysis or capture most of the data, more of the data, you can select the curve interpolation type accordingly. So if I select cubic spline, if it is missing certain values in the data, suppose from 1 to 2 seconds, it is linear behavior. So it is changing linearly, but from 2 to 3 seconds the behavior is different, and in order to smoothly transition of the motor, you need to add certain extra points. Those will be captured with the help of interpolation type. And then finally the expression. So if you have any predefined functions, you can define them with the help of this expression. So suppose abs, consider this value absolute of. So if your motor is behaving with respect to some function, from the various functions that are available here, you can select. So for the time being, we'll be selecting a constant speed motor and click on OK. So now the next thing is to apply a load of, let's say, 8,900 Newton. So that weight will be here, placed here. But since we are dealing with a rigid dynamics problem, it's better to apply the load on the planar side and define a load. Here you can apply the action only and action and reaction. So this type is the right action only load. Sorry. So this is the action only load. I can define the load in this on this phase. I can change the direction. If you are incorporating some type of spring load, that will come under the action and reaction load. Similarly, you can define the torque. Torque will also have the action only and action and reaction only. So the force relative to what? So this is the one important thing to understand here. So if I'm telling that assembly origin, so wherever the assembly origin is there, the force will be considered in that way. If I consider selected components, if some other components is moving, accordingly the force direction will change. This is what these two factors are. So you can define the force based on the fixed component. So suppose in this mechanism, the part you are defining your force in the fixed direction, fixed plate. So whatever may be the position of the mechanism or this crank, the force will be always in the one direction. It won't change its direction. If you change the force direction with respect to the moving part in your model, the force will change according to the movement of the part. And if some other moving part is there and your force is connected to some other part, so whatever the changes are happening in that moving part, the force will change its direction accordingly. So depending on what type of what your requirement is, you can define the force directions. Okay, so the 8,900 is the weight of the vehicle that we are going to apply. You can either apply it on this face or you can select the edge. So let's say I'll select this edge. When I select this edge, I need to define what is my reference for movement. So I'll select this. So I want the force to be always in the vertical direction. You can change the direction according to your need. So since weight will be in downward direction, always the weight will be applied like this. Now the next thing is to incorporate gravity into this. So gravity will be in the y direction. I'll select y here. And here you can see the gravitational arrow indicating in what direction the gravity is acting. So our basic procedure is done. The next thing is to simply run this study and see what kind of movement are we getting. Whether we have applied the okay, this should okay. So since you can see I have applied the motor in the wrong direction, it is going downwards. And when the parts start interfering with each other, so the simulation will automatically stop. So even though I have defined the time step for up to 5 seconds, the parts started interfering at this point, so that is why the simulation stopped. And it could simply change the motor direction here. Now it will move upward. It is solving now. Hopefully no interference is observed. I want to capture more of the study, so I'll simply increase my time frame to 8 seconds and resolve it. Okay, so now our simulation is done. So the next thing to consider, the very important thing is to see the results that we are getting out of this. Okay, so we need to find what kind of motor we can use for this particular purpose. So in the results and plots, select the type of category that you are interested in. So I want to find, let's say first the torque values that I am getting. So I'll select forces, go to motor torque, select components. So I'll select the magnitude, and here you need to select the motor. So this will define that X, Y, and Z based on the motor center. And plot result will be whether I want it frame wise or time wise. So I'll say time. So it will plot the result from 0 to 8 seconds. And I click on OK. So you can see initially the motor torque is almost 4,245. But as we increase the time, or the jack started moving upwards, due to the mechanical advantage provided by this motion, the torque requirement reduced. So basically we can assume that we will require a motor which will generate almost 7.5 Newton meter of torque. It is in Newton mm right now. Then the next thing is power consumption. We can also find that. So what kind of power rating will be, what kind of motor with the power rating we will require, that we can find out. Simply momentum, energy, and power. Select power consumption. In this also motor. Click OK. So the graph states that initially the motor will consume almost 76 watt of power. So I need to have the motor which will be able to generate this kind of power in order to consider the lifting of the car jack. One more small thing you can do is get the displacement by what distance this particular frame is moving. So I'll select displacement. I can tell it to trace path also, and click OK. Select one. Okay, so I need to define a reference point here. So I'll say this is my reference, bottom face. Okay, I need to select one reference point for this. So let's select this point. Okay, so it has shown me the path that it is tracing. Since this is linear to path, it is easy to understand. There are many mechanisms which may involve some complex path. Suppose cam follower motion. So in order to, you can also generate the cam with the help of this trace path method. So there's one more provision for cam synthesis in the SolidWorks using the SolidWorks motion. Okay. So I think you get the idea basically what we can do with the help of SolidWorks motion.